Concluding remarks regarding work. The similarity of the expressions for work in the three processes discussed in section 4 before and in the process in which work is done at the moving boundary should be noted. In each of these quasi-equilibrium processes, work is expressed by the integral of the product of an intensive properties and the change of the extensive properties. The following is a summary list of these properties and their work expression. The simple compressible system work stretched wire DL surface field system in which the work is completely electrical. DA. In all these programs, we have the integration of an intensive, the integrals of the product of an intensive property and the change of an extensive property, such as we have extensive, intensive, extensive, intensive. Although we will deal primarily with systems in which there is only one mode of work, it is quite possible to have more than one work mode in a given process. Thus, we can write the W a summation of various work, stretched work, surface tension work, and also we can write electrical work. dz. Here the dots represent other products of an intensive properties and the derivative of a relative extensive properties as said before. In each term, the intensive properties can be viewed as the driving force that causes a change to occur in the related extensive properties, which is often termed the displacement. So we have displacements terms. Thus, as we can derive the expression for power for a single force, for example, as this picture, this relation can, for the power, we have dt p dv on dt slash dl on dt dA on dt and minus dz on dt. It should be noted that many other forms of work can be identified in processes that are not quasi-equilibrium process. So for non-equilibrium process, for example, there is the work done by shearing force in the friction in a viscous fluid or work done by rotating shaft that crosses the system boundary. Force on due to friction forces. And force due to the system boundary, shaft cross the system boundary. The identification of work is an important aspect of many thermodynamic problems. We have already noted that work at the identified only at the boundaries of the system. For example, consider this picture, which shows a gas separated from the vacuum by a membrane. This picture shows a gas separated from the vacuum by a membrane. Let the membrane rupture and the gas fill the entire. At A, the gas separated from vacuum with a membrane. And B, rupturing the membrane. And gas, we can ask whether work is done on the presses. Does work done is the question. If we take as our system the gas and the vacuum space, at first we have So if we take our system, the gas and the vacuum space, for example this system be the gas plus vacuum space. So in this case we have no work because no change, no energy crosses the boundaries. But if we consider the gas as system, we do have change of volume and we may be tempted to calculate the work. The value. So we should calculate the work PdV. Is it possible? However, this is not possible. So equilibrium process. And therefore the work cannot be calculated from this relation. Because there is no resistance on the system boundary as the volume increases, we conclude that for this system no work is done in this process of filling the vacuum anyway, but we don't have no resistance as system boundary, so no work accurate in a non-equilibrium process. Another example can be cited with the shows in this picture as another example for work remarks. Another example can be cited with the aid of figure here. In this figure part A, the system consists of the container plus the gas with the specified boundaries here. Work crosses the boundary of the system at the point where the system boundary intersects the shaft, and this work can be associated with the shearing force in the rotating shaft. In the part A, so we have work crosses the boundary of the system. The boundary of the system. At the point where the system boundary intersects the shaft, this point A. And this work can be associated with the shearing force in the rotating shaft. In the part B, the system encloses the shaft and the weight as well as the gas and the container. Part B. Therefore, no work crosses the system boundary. As the weight moves downward, as we will see in the next chapter, we can identify a change of potential energy within the system, but it should not be confused with work crossing the system boundary. You have potential energy change in steam. We will discuss it in the next chapter. The next section, it is definition of heat in the next chapter.